Good afternoon, everybody. My name is Jackson Barnes, and I'm a second-year PhD student in the Department of Earth and Planetary Sciences. And today, I'm very excited to tell you about my research on the forming of tiny, tiny planets at the absolute edge of our solar system. First, I want to ask you a question. Have you ever wondered how the solar system formed? Well, maybe we can look at other solar systems, see how they formed, and then compare them to our own. Or we can simply look into our own solar system and look for clues there. That's what we're going to do today. But where can we find these clues? First, we need to start out with the sun. It's the center of our solar system about which the 8 planets orbit. We first have Mercury, and then Venus, and then we have the Earth, where we are. We're 1 astronomical unit away from the center of the sun, and all of the other planets are measured relative to this distance. Venus and Mercury are therefore at smaller AU, as they're interior to the Earth. Further out, we of course have Mars, and then we have the asteroid belt. This comprises the inner solar system. Now, we could look for clues in the inner solar system, but the formation of the inner solar system was way too chaotic to leave any good clues behind. So we need to move further out to the outer solar system, where we have Jupiter, Saturn, Uranus, Neptune, and of course, the dwarf planet Pluto, which is part of the Kuiper Belt. Now, the Kuiper Belt is a very special and important place, as this is where the clues that we're looking for can be found in the form of planetesimals. Planetesimals are very tiny building blocks which form up the planets. Now, before I continue on, you may note that Pluto is actually looking a lot bigger than Earth here. In reality, it's a lot smaller, about this big for scale. So if it's this big, then how big are the planetesimals? Well, let's take Pluto for scale, and let's take Arrokoth, which was visited by New Horizons NASA mission earlier this year. To scale, Pluto is approximately about 1,000 or 100 times bigger than Arrokoth, with Arrokoth being about 30 kilometers and most planetesimals being about tens or so kilometers, about the same size as Arrokoth. Planetesimals also come in a variety of different forms. They come as solitary planetesimals or wide binaries in which one planetesimal orbits another at a wide distance, or a contact binary, in which this wide binary is now touching and orbiting about a center of mass. But how do these planetesimals form? Well, we need to start out with a protoplanetary disk, or when the solar system was in its infancy. It started out as dust and gas. This dust and gas accrued to form planet pebbles. These pebbles formed planetesimals, and these planetesimals grew to form planets. And we're generally very familiar with how dust and gas form the pebbles and how the planetesimals form the planets. But we're not really sure how the pebbles form the planetesimals. This is where my research comes in. We need to ask ourselves these 3 questions, though. How do small pebbles make bigger pebbles? How do these pebbles form boulders? And how do these boulders and pebbles form planetesimals? We need to overcome some growth obstacles, though. When small particles moving at slow velocities accrete, they stick because they're moving at low enough velocities. But when they get bigger, they start to bounce off of one another. They break apart and come back together again, continually bouncing in this equilibrium state, inhibiting any growth. And if there are some particles that manage to get bigger and collide with smaller particles, they fragment each other, also inhibiting growth. So what do? What we need to do is have the most promising solution of gravitational collapse. This occurs when pebbles and boulders bound by gravity collide and accrete with one another to form a planetesimal. They lose energy, and as they lose energy, the particles start to lose their velocities and slow down, falling to the bottom of what is known as a gravitational well. Now, Michelle, if you could please bring this out. The simulation actually does provide you a good explanation of what a gravitational well is, but I think it'd be a lot better to show you what a gravitational well is in person. Thank you. So if we start out with a handful of pebbles, or planetesimals, we throw them onto this fabric of space-time, we note a small dent. And as we have more and more, we have a larger gravitational well. And as we have more planetesimals all hitting each other and accruing through gravitational collapse, we have a larger gravitational well, essentially simulating the growth of a planetesimal system. Thank you, Michelle. Now, let's go back to Arrokoth. Why did I mention this? Well, Arakoth is actually a very strong, or provides very strong evidence for gravitational collapse. We note that it has a similar composition, given the similar colors of its faces, which means it formed from a local environment, seen from that simulation earlier. It also has very few craters, which means it had a very gentle formation process. These are all indicative of gravitational collapse occurring in the outer solar system. And my research aims to create something similar to Arakoth, a contact binary. So what I do is I input 1,000 particles into a system, and I give them uniform radii, uniform masses, and 3 different types of velocities. And together with significant enough angular momentum, I'm able to create something like this, a wide binary system. Now this is super exciting because I'm able to create a wide binary system that also implies that gravitational collapse does indeed occur in the outer solar system. But it's not quite a contact binary. So what do I need to do in the future in order to make this happen? What I need to do is include more particles. With more particles, it will be more analogous to what's actually occurring in the Kuiper Belt. And I also need to track the thermal history of each of these particles, because there's lots of ices on the surfaces of these pebbles. And as they collide and accrete, they release a lot of heat, allowing these ices to evaporate, changing their masses and the system as a whole. So in the future, I'll be taking these into account. But for today, what I'd like you to leave with is that planetesimals and binary objects are everywhere. And in order for us to understand where we come from, we need to start small. Thank you very much.